So we want to take our computer and we want to put it on the FPGA now. All right. What we need to think about is what this looks like. First of all, the computer is just a component. Everything that you've done up until this point has been a simulation. The simulation has allowed us to drive in a clock and a reset, and it's allowed us to connect constants to the ports and then observe things on the outputs of the ports. But more importantly, it's allowed us to observe things in the CPU, namely the current state of the control unit and all of the data path registers. So by looking at things like instruction register, PC, MAR, A and B, we can see that the computer is actually running. Now what we want to do is say, okay, how do you put this in the real world? Well, the real world for us is going to be this FPGA. And what we want to do is we want to put this onto the DE0CV FPGA. And if you think about what's on the DE0, we have some I/O that we might want to use as our ports. Okay? So the key to this becomes, number one, you are going to have a top.vhd. Okay? Just like all the homeworks and labs up until now. The top.vhd still has the ports mapped to the I/O on the FPGA. Okay? So it's still going to use, hex 0, hex 1, red LEDs, and switches, and the buttons, and all that sort of stuff. So the top is going to represent the top of the FPGA. And what we want to do is we actually want to put our computer inside of it. You do not mess with anything in your computer other than your program at this point. Don't wire anything inside of this. Just instantiate it as a component. Then the question becomes, what do we connect to it? So what we want to do is we want to bring in real I/O from the outside world as inputs. If you look at this FPGA, really the inputs that, or this FPGA board, really the inputs that we've been messing with are really the switches. So we have 8 switches, and other than that, you could bring stuff in on the pins, I guess, but then we'd have to drive it in from like the analog discovery, so that's going to be a lot of work. So what we could do is, let's just use this as kind of our main inputs, and then we can also, we have 4 switches, or 4 buttons. We can go ahead and bring those in too, but that's really all the I/O that we're going to use to demo our computer. And so what we do is we bring in switch 0 to 8, the 8 switches, on port in 00. Now, if you recall, port in 00 is what address? It's actually at F0. So that means if we want to access the switches, all we do is do a load direct from address F0. The switches, or the keys, the 4 buttons, what we need to do with them is concatenate them to 4 zeros, since there's only 4 bits of them, and we'll bring that in on port 01, which is addressed to F1. Okay, then you look at what I/O do we have, what outputs? Well, we have the red LEDs, of course, so those are ones we want to drive. So let's go ahead and put those on port out 00. What address is that? Anybody remember what that is? That's going to be, it's going to be E0. Now let's drive a hex display. Well, you remember the hex display? We want to actually drive something meaningful to it. So why don't we take a single 8-bit port, and why don't we break it up into 2 4-bit nibbles, and we'll drive those nibbles through 2 of our card decoders that we developed. And so, for example, if I write to port out 01, I'm going to drive 2 card decoders, and I'll drive hex 0 and hex 1. So whatever I write to that port, whatever I store to port 01, it will show up on hex 0 and 1, and it'll actually show me the hex information. So that'll be very handy. So at that point, it's like, why don't we just do that for the other card decoders? So let's go ahead and make port 2, hex 2 and 3. We'll make port 3, hex 4 and 5. And then just because we can, let's go ahead and hook port 4 and 5 to the pins on the GPIO header. That way, if we wanted to ever look at something with the analog discovery, we could do that. Okay? What's key here, though, is that we can run the computer very fast. And even though we're walking through the state diagram to do things like load A direct, it takes multiple states, right? It takes like 8 states to do that. So if we run the clock really slow, it'll be like tick, tick, tick. But if we run it really, really fast, we won't even notice that the state diagram is blasting through its states. Okay? But we do want to slow it down so that we could potentially see it actually moving very slow so we can make sure it's working okay. So what we want to do is let's go ahead and instantiate our precision clock divider. Okay? Now, when I look at that, I've got my precision clock divider here, and I want to drive 2 control lines to it. Where are the control lines? Well, if you think about it, we'll bring in switch 9 and 8 as the control. And the reason I do that is I want to have just the lower 8 LEDs show up, and then I want these guys to change the clock frequency. Okay? So that's the best way to do it. That's going to allow me to slow down the thing and actually see these things walk through the instruction execution. Okay? All right, how's that feel? So that's what you're going to end up doing. Now, if I go ahead and look at what the top might look like, let's take a look at that. So here's my top. I have clock reset and switch, and I have 0 to 9. 8 are going to be for the red LEDs. 2 will be for the precision clock divider. And then I'm going to have LEDR, and I'm going to have my 6 hex decoders. And then I haven't put in my GPIO yet in this version, but you would put that in there if you wanted to go for the gusto. And you're going to have components. Car decoder, we're going to declare that, of course. We're going to declare clock division precise, and then you're going to declare your computer. Where would be a good place to go look to find a nice declaration of the computer? Because this is a lot of typing. In the computer entity would give you the port definition, absolutely. But you know what else would work? What if you went to your computer test bench? The computer test bench instantiated the computer for your simulations. You could go get the declaration in one copy paste. Okay, that's cool. And then what you got to do is you got to go create all the signals that are going to be used to route to that instantiation. Okay, so here you start seeing some things where I need to instantiate my clock divider, instantiate, this and that, and then I instantiate my computer. All right. The way that I did it is for clock and reset, there are internal signals called reset, and then I have an internal signal called clock slow. That comes from my precision clock divider. Okay. Every one else of these input ports, what I ended up doing is I created input signals that I could connect to them, because guess what? Not all the input ports to the computer have something driving them. If you think about what we actually did, we have 2 through 15 are not connected to anything. But you can't declare a component unless you're wired up. So we're going to have some dangling wires in here, which is fine. And then let's see. So we did that, and that's it. Your top level is very uninteresting. All it does is just wire up a very, very simple computer. All it does, if you think about it, there's no functionality. You declare computer, you declare 6 car decoders, you declare precision clock divider. Top.vhd is actually quite trivial. You just wire it up. Then the question becomes, how do you run your program? Well, we are going to test the basic instructions. You don't have to test actually all 4 of the basic instructions. So what I ask you to do is this. Let me show you the test program that will exercise and show that your computer is actually working. I'm going to go look at my ROM, and I want to look at this program. I am going to start by doing a load A direct with F0. What is that? What is load A direct with F0? If I go look at my top, and I have it sitting right here, if I look at that guy, what is F0? Woo. It's the switches. So when I execute that instruction, I brought in the switches. So I can sit there and I can change them, and it will load from it. Then what I'm going to do is I'm going to store that, of course using direct, to some addresses. Well, if I store that to E0 in my next instruction, where's that going to go? That's going to go to the red LEDs. Okay. While I got it, when I store, I don't blow away the register A. It's still got the information. Why don't I go ahead and store it to all the output that I have? So let's go ahead and store A again to E1, store it again to E2, store it again to E3. And what that will do is it'll drive the binary value to the LEDs, and then it'll show me my value on hex 0 and 1, hex 1, 2 and 3, and hex 4 and 5. And they'll be the same. They'll actually be the same values. Then what I got to do is branch always, because I want this computer program to run. So what I'm going to do is I'm going to do a branch always up to 0. Now when I did this program, I only used 3 instructions. I used a load A direct, store A direct, and a branch always. But that's fine. That's all you need to do for part 3 because a whole lot has to work. Okay? A whole lot is working if this program runs. Okay, so now for that program, let's go ahead and take a look at what it would actually look like on the FPGA. Now I'm going to come along is I can go ahead and put all my switches to 0, and I have my clock set at the slowest frequency possible. So I'm sitting here and I'm waiting for it to do something, but think about this. I have my clock set at the slowest frequency possible. How fast is it moving through each state? Well, it's 1 second, right? So I have I'm going to reset it. I have it 1 second. It goes through fetch 0, fetch 2, fetch 0, fetch 1, fetch 2, decode. Then it goes execute, LDA, direct, 3, 4, 5, 6, 7, 8. It takes like 8 seconds just to get through the first instruction. So what I can do is I can actually see this thing kind of move a little bit faster if I change the clock frequency. Okay? So now, let me change this clock frequency. Okay, so now I've changed it to be a little bit faster. Hang on, I'm going to do a reset. Look at what, I'm holding the reset button down so you can see what I'm doing with the switches. I'm going to go ahead and I'm going to change this switch right here to be a 1. And I'm going to let go of the reset, and I'm going to watch this thing show up. So I've got this as a 1, this is a 1, and this is a 1. And look at what happened. Notice that it took a minute. Let me do reset again. It's sitting there doing load A direct, then finally it does a store A direct, and then it went store, 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 store. Let me change that to be even, I don't even know how much slower you can get. You go slower than this, it's like almost aggravating. So let's see if it'll sit here. This has taken like 8 seconds to go. These are going to be my clock frequency guys right here. It's coming in here and I'm doing this load A with direct, and it's slowly getting one. Oh, finally got through the load and the store to the first address, which was E0. Now it's going through the store A direct to the next address, which was E1. Now it's going through the store A direct to the next address, which is going to be E2. And it takes like 7 or 8 seconds for this thing to do it because it takes a second for each state. But the reason that that's so cool is because you can see each instruction being executed. Now, it's super annoying, right? Let me change my clock frequency up to something very fast, and let's see if I can change these and have them update almost immediately. Okay, look, can you see that that's trickling through? So that's where I'm running my clock frequency at 100 hertz. Now it's doing a lot of states right there, but you can still see it trickle through. Do you see what I'm doing here? I'm changing the value and it trickles through all of them. I got my clock frequency at 100 hertz. It's doing 100 clock cycles a second. But how many states does it have to go through to run this program? It's like 7 or 8 states for a load. No, it's 8 states for a load, 7 for a store, and we did 4 of those. So we're running like 50 or 60 states, and then we run this at 100 hertz. It takes like almost close to a second to actually get through the whole program. Now I'm going to run it. I'm going to run the clock at 1 kilohertz. Okay? So now I'm full out. At this moment in time, it's instantaneous. I'm still running 50 or 60 states to pull this off, but look at what's happening now. I can change this, and it's instantaneous. You cannot see with the human eye or your human finger that this thing is running through all these different states to accomplish something this simple, okay? And it's because it's going so fast. And this is hopefully where you go, oh, a computer does really simple things. It takes it a whole lot of states and clock cycles to pull it off, but as long as I run the computer clock frequency super, super fast, it will do things that respond to a human who moves quite slow in a fashion that we don't even notice, okay? So what do you want to do for your demo? This is demo for part 3. If you look at the handout, what I ask you to do is you come into this part 3 and I ask you this. I say, implement your computer on the FPGA board. Okay? You should continually read from switch 7 or switches and write to LEDR hex 10, hex 32, and hex 54. Okay? How's that feel? Pretty awesome. Here's what the demo, though, I want you to look. Here's the demo I want. Number one, we need to don't run it full out, because then I can't tell whether you actually implemented a computer or not. You could have just done wires, right? So I want it slow, but I don't want 1 hertz. I don't want to have to wait 80 seconds for the thing to actually get through its program. Even when I run this at 10 hertz and reset it, and I look at it, I'm like 1001, 1002. That's pretty good. That's pretty good. But you know what's even better than that? Run that puppy at 100. Bam! Now I need to know that you're actually responding. So I change that, change that, change that. I can run through 3 different inputs on this in something less than 3 seconds. How's that feel? Yes. Now that is the demo for part 3 of the project.